I want to record this just because this is complicated. There's only two parts. So muscle system is complicated in general, but we're going to look at the muscle tissue, right? Muscles you will discuss in the lab, but here's the muscle tissue, what the muscle is made of and how the muscles are able to create a contraction, flexion, extension, and all other movements in the body. So there are three types of muscles. So there's a skeletal muscle, there's a cardiac muscle, and there is a smooth muscle. So we're going to skip on the cardiac muscle and smooth muscle, and we're just going to concentrate on the skeletal muscle, right? So this is the cardiac muscle, this is the smooth muscle, but just because that's the AMP1, we're just going to concentrate on skeletal muscle. Skeletal muscle, as the name implies, it performs the movement of the skeletal system, so it moves my bones. It is voluntary type of muscle, right? So, well, the nervous system can override, obviously, but it's voluntary, right? So that's my decision to do this, right? Cardiac muscle, involuntary because it beats on its own. Unless you relax, you kind of can't slow down the contraction of the muscles. Smooth muscles are within the blood vessels and within the digestive system, so also involuntary, you cannot control them. So with the skeletal muscles, you are in control, and they are controlled by the nervous system. So the nervous system basically controls everything. So I quickly explain what is a neuron. So it's controlled by the nervous system. So here is a neuron. Through neuron cable, we send electrical impulse from one place to another place. This is a cell, like any other cells. Muscle cell is elongated. Here's the muscle, the entire muscle. Here's the muscle cell. So it's elongated, like other cells are round. It depends, right? So function, shape relates to functionality. So here we need to send electrical impulse where? To a target organ. What is the target organ? Muscle. Where's this located? Within the central nervous system. Here's the brain, here's the spinal cord, right? And here's your muscle. Outside of the central nervous system. Central nervous system. Brain and the spinal cord, that's where the central nervous system is, and we're sending electrical impulse to your muscle outside. So this muscle is the target organ. We can send an electrical impulse to other organs, not necessarily to muscles, like to kidneys, for example, to release a particular hormone. So when we say target organ, that's the neuron that targets a particular organ. So here at the end, we have a muscle, right? Muscle belly, right? When it flexes, there is a belly, right? So the neuron sits on top of the muscle belly sits on top of the muscle, innervates muscles throughout the different parts of the muscle tissue. With yellow, we represent the nervous system. Muscles are highly innervated and highly vasculated. There's a lot of oxygen, and there's a lot of blood vessels, and there's a lot of nervous tissue within the muscles. There could be hundreds of neurons going into one muscle, or could be just as few. So here is a neuron. This is a cell body of a neuron. This portion is called axon, a cable, right? You have a wire, cable. And here, axon terminal that creates a junction. Junction is a connection. So think of an electrical cable, right? Electrical cable comes into the room and comes to that fixture. And that light, that switch, can control a particular fixture. Another switch can control another fixture, and so on. Similar with muscles. Whatever the muscle is controlled by different types of neurons, right? Whatever the neuron fires its electrical impulse, the muscle will be activated. For this neuron to fire, send electrical impulse, or to create an actual potential, action, potential. Action potential means sending an electrical impulse or firing. Fire or action potential. We abbreviate is AP. We need to stimulate the cell body. We need to bring the stimulus. Stimulus could be pain, loud sound, bright flash, or I'm trying to raise something. So I'm engaging a few muscle fibers. Let's say I'm engaging one muscle, or engaging few muscles, or engaging the entire system, right? It depends on the stress, on the stimulus that I'm creating. So when I create tension, I stimulate all these neurons because the cell body receives a stress, receives the stimulus, and sends this electrical impulse or action potential towards the muscle. And here we will communicate. Here we will release a lot of chemicals that will stimulate the muscle. And the muscles are stimulated by release of the neurotransmitters. So the way neuron communicates with muscle, or neuron communicates with another muscle, with another neuron, it could be neuron to neuron, or neuron to muscle, or neuron to organ, doesn't matter how. At the end, within the axon terminals, here we release chemicals. And these chemicals are called neurotransmitters. You've heard of dopamine, serotonin, norepinephrine, epinephrine, acetylcholine, right, for the muscles. Who was that person? Yes, great. Acetylcholine, definitely with the muscles, right? So these are the neurotransmitters that will excite this muscle. So the muscle will, or initiate a cascade of reactions. That's what we're going to look at. So this is a preview, and I'm going to only go through two important phases. So here's the muscle. This is important, right? I can put check marks everywhere here. So here's the muscle, and this is striation of the muscle. Muscles are striated. There's levels and levels and levels. So here is the entire muscle, and muscle with the tendon connected to the bone. So the muscle is made out of the fascicles. So this is the fascicle, this is the fascicle. There's a bunch of fascicles. Like a Russian doll. You pull one thing out of another thing, out of another thing. So muscle made out of the fascicle. Skeletal muscle made out of the fascicle. Fascicle is just a bundle of muscle cells. Or muscle fiber. Muscle fiber and muscle cell is the same thing. I can say muscle fiber, or I can say muscle cell. Same thing. So fascicles made out of the muscle fibers. Right? Here's the muscle fiber. So here's one fascicle. You just pull one fascicle. But there's a fascicle 1, fascicle 2, fascicle 3, fascicle 4, doesn't matter. So one fascicle could be excited, or another fascicle could be excited, or another fascicle could be excited in this arrangement. It could be one neuron going directly here, another neuron going directly here, another neuron going directly here. It depends on the arrangements. It depends on a lot of things. And then out of the fascicles, right, we pull the muscle fiber, but muscle fiber is also made of something smaller called myofibrils. Myo means muscle. Sarco means muscle. So the muscle cells or muscle fibers, here's a single muscle cell, right? Here's the muscle out of one fascicle, right? We can have a bunch of muscle cells. 1, 2, 3, 4, 5, and so on. So, and then muscle fibers are made out of the bunch of myofibrils. Fibril, fine protein type of tissue. Contractile element. We're going to look at this. And then myofibrils are made of something smaller, even smaller. Filaments. So here's the muscle cell. Then here's a myofibril. 1, 2, 3, 4, 5. And then myofibrils are made out of the thin and thick filaments. Actually, would be thick filaments and would be thin filaments, like that. You'll see the image later. And on this level, where the contraction actually happening. We're going to get to this. So please know this arrangement. Muscle, fascicle, muscle fibers, myofibrils, and filaments. It's important. And each division, well, 3 of them, separated by the membranes. Not, well, it is good to know, but. So the outer layer, or the outermost layer of the entire muscle, is wrapped around by epi on top. Mysium, mysa, muscle, related to muscle as well. Myo. Epimysium, not mysium, but epimysium. Right here, I don't know if they're showing here, I don't see it. Right here, epimysium. Right, around the entire muscle. Then perimysium around each fascicle. Fascicle, because muscles are made out of fascicles. Right, perimysium, one fascicle, another fascicle. And then, so endomysium wraps around individual muscle cell. Because muscle fiber, same as the muscle cell. So here, you have a muscle cell. This is the entire muscle cell. Then pull out of the fascicles, right? Let's say fascicle has 20 muscle cells, right? We just pull one muscle cell. And muscle cells are made out of the myofibrils, myofibril, and myofibrils made out of the myofilaments. So in each muscle cell, surrounded by triads, so the triads we call the cisterns. So here's the cisterns, here blue stuff. Then there's the T-tubules, gray, and here is the sarcoplasmic reticulum. So this is the sarcoplasmic reticulum, this are the cisterns, and this is the T-tubules. Within the sarcoplasmic reticulum, we keep calcium. Then the calcium will be pumped into cisterns. From the cisterns, calcium will flow inside to get towards myofilaments. So each muscle cell wrapped around, besides the endomysium layer, the most important layer, I put the blue dot here, is called sarco, related to muscle, lemma, membrane. Sarcolemma individually wrapped around each muscle. So this would be a sarcolemma. Muscle fiber and the sarcolemma, let's say this is endomysium, and the sarcolemma would be outside. On top of the sarcolemma, if this is the sarcolemma, that's where the muscle, that's where the neuron would be sitting on. It's not really touching it. It's like this. So here's a space. And within the space, right, so we release chemicals. We'll get to this. So it basically would be sitting somewhere here. Right, if the membrane, we'll put it there. We call that region, right, because the axon terminal is sitting on top of the muscle. We call it neuron because this is the neuron. This is the muscle, neuron, muscular junction, connection. Or the terminals, termination. Like when you drive to the bus depot, that's the terminal, that's the end. There's no place to go. When the electricians work on the electrical cables, they have big panels, they terminate their cables. So they have wires, so they terminate. So the neuromuscular junction, or the terminals. So the sarcolemma. And you see the sarcolemma, the entire muscle fiber, muscle cell, made out of the bunch of myofibrils. So obviously, if this muscle cell contracts, all of the myofibrils must contract. Again, all or none. But the contraction actually happened on this level, on the myofilament. Myofibrils and myofilament, that's where we're going to. You see there's like striations. So these muscles are striated, like lines, striations. So here, something that is called Z-disc, and here's another Z-disc, and here's another Z-disc. It just shape looks like that. That's where the myofilaments connected to. So one Z disc, another Z disc, and myofilaments are connected to. And that's where the contraction happens. And then there's another Z disc, because muscle is very long, elongated, and that's where the contraction happens. You can see it here, Z disc and Z disc within myofibrils. This is called sarcomere, contractile unit of a muscle. Yeah, sarcomere. So the sarcomere is a contractile unit of a muscle. So now if you're gonna look at the striations here, so I can say this is sarcomere, sarcomere, sarcomere. So these little things, right, striations, are each sarcomere. And Z, that's where the myofibrils are connected to, like a spring, like a coil. So the sarcomere is a contractile unit. So these are the myofilaments. So here are the thick filaments and there are thin filaments. So the thick filaments are called myosin and the thin filaments are called actin. That's where the contraction actually happens. In reality, again, I don't know, but there's connection. They're not floating in space, like connected like that. So the thick filaments are the myosin and the thin filaments are the actin. So the thick filaments, myosin, have myosin heads, like that. So for the muscle to contract, myosin heads has to connect or create a cross bridge with an actin. Myosin head and the actin. Myosin head creates the cross bridge or the connection with the actin and changes the shape. When it changes the shape, right, that way, connects like this and then changes the shape towards the midline. So when it changes the shape towards the midline, this is the myosin actin would be pulled towards the midline, M line. And the contraction happens. So the entire system, and this is the entire sarcomere, the working contractile unit of the muscle, would contract. And that leads to muscle contraction. Just because this is very tiny and the muscle is very long and we have thousands of sarcomeres, that's how the muscle contracts. That's how complex this thing is. So every time we're doing any type of movements, or even standing right now, I'm creating partial contraction called tension. You're sitting, just because you're sitting upright, partial contraction, tension. Muscles are constantly engaging. This constantly happens. So the myosin heads create the cross bridges with the actin. They change the shape and they pull this towards. Then they relax, then they disengage, that calls the relaxation, then they engage contraction, relaxation, contraction, non-stop, millisecond. So myosin, thick filaments, actin, thin filaments. So this is all proteins, all of it made out of the proteins. That's why we constantly say, well, when you need to build muscle or to sustain your health, you need to eat protein, right? Amino acids. That's a material you consume, so you use it. So you see this muscle is relaxed because you see this on the scan. That's kind of light band here, and there's a disc right there. So that muscle is not contracted. You can see here as well. They're not contracted, but when the muscle contracts, so they're not showing the engagement of the myosin heads to the thin filaments here. So, but they are connected here. Here you can see it. And then actin would be pulled towards the midline. They slightly overlap. So just remember the discs. So that's where all of the filaments connect. So and each sarcomere would be pulled not independently but all together. That's how the muscle contracts. So here's a blowout picture. Myosin heads. Myosin with myosin heads. And then the actin with its active side. Looks like a blueberry. This fossa, depression, that's active side. So the myosin head must create the cross bridge with the actin's active side. So please remember 4 players here. Myosin, actin, troponin, and tropomyosin. So you see the bunch of thin filaments acting, They have tropomyosin and they have troponin. Tropomyosin in green is just a wire that covers the active side. You see it kind of blocks like that, blocking it. So, and the troponin, like a pin, goes through this wire, through the tropomyosin. So let's say here's the active side, like that. Here's a tropomyosin, and here's the pin. Pinches the tropomyosin. So the tropomyosin cannot slip out. So the tropomyosin, the wire that is pinned by the pin, it's blocking the active side. So the myosin heads cannot create this connection here. So you cannot contract the muscle. For the muscle to contract, you need to pull the troponin out, the pin. Calcium pulls troponin out. When the troponin is out, tropomyosin slides off. And when the tropomyosin slides off, now the active sides are open. And the myosin heads can create this engagement. Not complicated, right? Yeah, simple. So just know these players. Tropomyosin, troponin, actin. You already know actin and you already know myosin. And there's like two of them, two, going in different directions. So the ATP would be engaging here. So the ATP will disengage and ATP will engage as well. So the ATP will change the shape and then ATP will pull it out. So let's look at all 4 steps or 5 steps. So action potential is an electrical impulse, stimulates the calcium release. Calcium binds with the troponin, right? Let's say troponin like this. Calcium binds with the troponin. Troponin will be pulled off. The tropomyosin slides off. And these heads create the cross bridge with acting active side. And the power stroke, this bending, right, will happen. So this is a excitation coupling or the power stroke mechanism. Excitation, coupling, or the power stroke mechanism. And contraction occurs. The second step, and there's a step that precedes all this, initiation, neuromuscular junction. All right, so neuromuscular junction, that's the first step. So here's the muscle, here's your sarcolemma, the muscle cell, here's the sarcolemma, here's the neuron. So, and here's this axon terminal right here. So there's also 4 or 5 steps, however you want to look at. I don't know. So here's the muscle, right? That's the axon, cell body, axon terminals. So the electrical impulse or the action potential always goes away from the cell body towards the target organ. Here with the axon terminals, if you look inside, we have vesicles like storages, like with yellow stuff in there. So inside here, we have something called neurotransmitters, acetylcholine, ACH. Acetylcholine, that's a neurotransmitter. Dopamine, serotonin, norepinephrine, epinephrine, different types of neurotransmitters. In this case, within the muscles, that's acetylcholine. So when this electrical impulse arrives to the neuromuscular junction, calcium flows inside. So there's a storages. Neurons make acetylcholine and store it here at the neuromuscular junction. It's constantly being made. You're making it and you're storing it here, non-stop. So the calcium, it's positive, that's an ion, it's an electrolyte, conducts electrical currents, gets inside of it and releases acetylcholine out of the storages. So the calcium acts on these vesicles and they release acetylcholine. See here? This yellow stuff is being released. And here are the channels. Here are these fibrils. Here are the filaments, these little dots. Here's this electrical impulse that travels through the T-tubules that stimulates cisterns to release more calcium. Calcium here and calcium there. Here calcium pulls the troponin, here calcium excites the vesicles to release acetylcholine. So the calcium enters, acts on the vesicles release acetylcholine, and this part is called a, well, when the muscle, when the neuron connected to the muscle, we call it synapses, connections. It's like one neuron can be connected to another neuron, synapse. Synapse is just a space in between two neurons or in between muscle and the neuron. Space right here. So this space would be synapse. And just because it looks like wavy like that, it's called cleft. Like babies are born with cleft, right? So that's where they got this name from, synaptic cleft. And this is the membrane sarcolemma, and this is the sarcolemma. So the sarcolemma, you see, changes the shape here, where there's a plate, end plate. So this are the channels. To enter inside of the cell, you have to pass through the channel. So the calcium stimulates acetylcholine. Acetylcholine is being released, and acetylcholine binds with the channel. These yellow bubbles sitting right on top of the channel. Sodium, as soon as the channels are open, sodium will enter the cell. And then potassium will leave the cell. Sodium enters, potassium leaves. Both of them are positive. Sodium enters, potassium leaves. Action potential, calcium, acetylcholine, sodium enters, potassium leaves. So here, let me make it differently. Right? Synaptic cleft. Here are the channels. Acetylcholine is being released from the vesicles, binds with the channels, and that helps to bring sodium inside and potassium outside. Action potential, calcium, acetylcholine, and then there's exchange, sodium inside, potassium outside. That's the neuromuscular junction to initiate, to open these channels. Because the myofibrils, right, and filaments are here. This leads to step number 2, power stroke. In power stroke, we release calcium. Calcium pulls troponin out. Tropomyosin slides off. And that leads to a cross bridge between actin and myosin. Complicated, but not complicated anymore, usually. So let's go back here. So sodium and potassium. And that's a precursor for the nervous system, but it's also important here as well. Here's your cell. There's more sodium outside, and there's more potassium inside. For this, because when the sodium enters, here we show at the same time, sodium enters, potassium leaves. There's a delay. Sodium enters first, action potential is created, and then potassium leaves. So there's 3 terms, or 4 terms. Depolarization. Depolarization, it's when there's activation or the release. Then repolarization, a reset. And let's say polarization. depolarization set. So I am polarizing. When I let it go, I depolarize. Let's say a bow and arrow, right? I'm polarizing, setting the stage. I let go, the arrow starts flying. I'm depolarizing, but now I have to reset, repolarize. Polarization, depolarization, repolarization, right? I have to create a kinetic energy. I need to create a set, right? So when this thing marker lays down here, there's no kinetic energy, right? So there's no potential energy, I'm sorry. So I need to create this potential energy. I have to raise it here. So I'm polarizing, I'm setting the stage. So these ions, they in their places. As soon as I depolarize, this ion starts moving in different directions. And then I will repolarize, I have to put them back at their places, like restart. So full start, and then you go back at the starting line, start everything again. They constantly move. There's also calcium and some other electrolytes that will balance the charges. So when the sodium enters, that leads to depolarization. When the potassium leaves, that leads to repolarization. So the sodium depolarizes, creates another action potential. So when the stimulus is strong enough, not only here I can open channels, I can also open channels here. By opening channels here without even the axon terminal sitting on top of here, I can bring more sodium here. So, and all of the sarcomeres with the Z discs that all over the place throughout the entire muscle will contract. So the contraction would be very, very strong. So the depolarization, repolarization. Polarized state, right? Depolarization, sodium enters, and repolarization, potassium leaves. That's what happens inside of the cell. Muscle cell or the nervous cell. When it's polarized, it is minus 70 millivolts. We run on electrical impulses. We run on electricity. So that's polarized state, minus 70. When sodium starts entering, and sodium is positive, you bring more positive, you become less negative, or you become more positive. By bringing more positive into negative, you travel here. And that's depolarization, meaning that creates a contraction of the muscle, for example, or send an electrical impulse. That's how the electrical impulses are generated. By bringing more sodium inside of the cell, from minus 70 you travel up to plus 30. Now you cannot create another contraction. So for the muscle to have a contraction, you have to travel through the entire set from minus 70 to plus 30, approximately. So sodium enters. Now it's a lot of sodium inside, positive. How do you reset all that? Just because potassium is sitting within the cell, and potassium is positive, is sitting here, all you have to do right now, just because you're plus 30, you're removing positive. And when you're removing positive, you're going back to negative. You go from more positive to more negative. And that's repolarization. So polarization, polarized state, to fire, you have to reach minus 70, sodium outside, potassium inside. Sodium enters, positive enters, so membrane is negative, you make a membrane more positive or less negative, traveling to plus 30. And now you're removing potassium, right? And you're going from plus 30, you're going back to minus 70. If there's leaky channels, so there's more potassium constantly flows in, so they kind of establish the membrane potential. So they establish it because the leaky channels constantly moving in and out constantly. So if too much of potassium leaves, you can go to minus 90. And it's usually what happens. Here's kind of delay. So you have one impulse, you go through the entire cycle, you cannot generate another contraction of the muscle unless you will get somewhere to minus 70. If you get to minus 90, it's called refractory period, meaning that you cannot generate another potential even if the stimulus is there, because you have to go back to minus 70, approximately. So minus 90, what does it mean? I just remove a lot of positives, right? So that's why I'm too negative. This is the hyperpolarization, right? You're hyperpolarized. So there's no another impulse could be generated. So any questions on this? I can stop, right?